Alright guys, so we're going to do some more collisions of things of like and unlike velocity and mass. So I have these toys that are, and I had to make them both the same mass, that's why there's the mass on top of this one and that one. So the idea of these is that there's fans inside of them, and so if you put them on a level surface, they'll kind of float on a little bit of air, so it's like it's frictionless. And what I'm going to do is I want you guys to predict what will happen if I have equal masses colliding. Will the one stop and the other one goes? Will they both go with a small velocity? Will this one bounce back? You want to make a prediction based on that. All right, so I'm going to put them down here. I'm going to turn the one on. It's just kind of floating there. I'm going to turn the other one on. It's just kind of floating there. And if I send the one moving at the other one in 1D, the same mass one should stop, and the other one should continue on with the same velocity. So our picture here should have a large arrow on the second one and no arrow at all on that one. All right, what if it isn't a direct hit? What if I don't have it just in line? What if it is a glancing blow? What do you think will happen to equal mass soccer balls that are colliding? So write down your prediction. Again, I'm going to pan this down, try to do the stuff right below. I know this isn't ideal, but hello. All right, so I'm going to have a glancing blow here at an angle. And what we should have seen is that one would go up while the other went down at an angle. If we consider the individual components, this did not have momentum in the y direction to start with. That means that this one can't either. So if I consider their y components, these would have to cancel out. The x components of these dotted arrows here, if I added those together, they would add up to the original arrow. We're saying that we have no friction in this. All right, so we also have a baby one that is much less massive. So I want you to predict what's going to happen when the little one collides with the big one. And again, this will be a 1D collision. All right, so what we should have seen is that the little one rebounded, and the big one moved a little bit. Why did that happen? Because when they collided, they had equal and opposite forces. So the same force on the little one was enough to cancel out this velocity and send it in the opposite direction, and that same force on the big one was just enough to give it a little bit of velocity to the side. All right, let's flip this situation around. And we're going to collide the big one with the little one. So write down what you think will happen in this case. Okay, so looking at this one continued on a little bit slower maybe, but almost like it didn't encounter the little one. The little one jumped off. It really went a lot farther. All right, so I have the original dynamic cards from the school. Which are these? These are of equal mass. One of them has a spring plunger in it, so you can push this in and it can push out. They're of equal mass. The other side of this one has a metal bar I can put this against. I want you to predict what's going to happen when I release this. How will their velocities compare, and how will their speeds compare? So their speeds should have been equal because they have the same mass. The velocities will be equal only in magnitude. And they end up being opposite in direction. So it's opposite in direction. What if I change the masses? So I'm going to double what the one mass is with a weight. And now when I put these together and release them, the more massive one is much slower. If it is double the mass, the big mass should have half of the velocity of the little one. In magnitude, so it's going to have and it's going to have an opposite direction. If I add these velocities together, they're not going to equal 0 anymore. So I'm still going to have velocity in the little one's direction. That's not going to cancel out. All right, I have a fan cart that has a plastic partition that can come off. We're going to make predictions on what's going to happen when I just turn it on and what's going to happen when I turn it off and take the plastic partition out. I'm going to have to relocate you guys because the floor is not level enough for this. All right, so I'm going to turn this on with the partition in. And nothing is going to happen. Now I'm going to take this out of the way. It's going to expel air this way. And we can see that our cart accelerates in the opposite direction that it's pushing the air. So this is going to be how rockets work. All right, last one. I have 4 balls here. I'll keep them towards the middle. I have a ball here that I'm going to roll down. The last thing that you want to predict is how far the ball will roll up the other end. There is friction. Things do not roll without friction. I'm going to release this with no velocity from the top, just by removing my finger. And if you watch closely, the ball ended up in the green container. All right, the last little bit you guys missed today would deal with inertia related to momentum. So inertia is going to be how difficult it is to accelerate something. And this is dependent completely on this object's mass, and mass alone. That's going to be different from this section, which is going to be momentum, because this is going to have mass times velocity. So this product. This is designated by a lowercase p. It's equal to the mass times the velocity. The units are kilograms meters per second, so we don't get a new unit out of this. If we talk about change in momentum, it's often written as Newton seconds, which is the same. And this is a vector, so we'll have to break it into components. So there'll be a direction associated with it.